Okay, bon, bonjour. Et comme j'ai dit la dernière fois, puisqu'il y a des gens ici qui ne comprennent pas le français, les postdocs, je vais parler en anglais. Hein. Et les derniers cours que j'ai donnés ici, il y a quelques années, c'était en français. Mais maintenant, bon, je vais changer pour l'anglais. Alors, les buts de... Ça, c'est encore en français. Hein. Le but de cette leçon, alors, c'est l'extension quantique de la théorie de Kramer-Rao-Fisher. On a discuté dans les premiers cours la théorie classique de Kramer-Rao et Fisher, de l'estimation des paramètres. Ici, on va étudier les rôles de l'intrication. On va montrer que l'intrication est importante pour augmenter la précision de l'estimation. On va discuter aussi les applications de cette théorie quantique générale en interférométrie optique et atomique, et aussi à l'analyse de la méthode connue comme amplification des valeurs faibles, weak value amplification. So now for English. So let me just remind you of the main result of the last lecture. We showed in the last lecture, just using classical arguments, that the standard deviation in the estimation of some parameter x, which is part of some dynamical system, is bounded below by this expression here, where n is the number of repetitions of the experiment, and f of x is the Fisher information, which depends on the probability of getting the several experimental results j. You have to sum that over all possible experimental results. Now, for continuous measurements, this expression here is replaced by this one. And this, you see, this is the probability of getting an experimental result psi if the value of the parameter is x. And of course, this means that this integration here is an average of this expression over all possible experimental results. Okay, so that's the classical Fisher information. Now we go to quantum parameter estimation, and the initial idea is the same as before. So we want to estimate some parameter that is part of a dynamical process. So we send a probe through this dynamical process, and one measures the final state of the probe that interacts with the system in order to determine the parameter. Now, the novelty here is that the precision in the determination of the parameter now depends on the distinguishability between quantum states corresponding to nearby values of the parameter. And one knows that if one changes the parameter, the corresponding quantum states may not be orthogonal to each other, so we have a different situation here. However, I'll show you that quantum mechanics not only presents this difficulty in the estimation of parameters, but also can enhance the estimation of parameters by typically quantum mechanical effects. Now, so let's see how that applies to to optical interferometry. In this case, for instance, suppose we use an interferometer with a coherent state, and we want to differentiate a coherent state with displaced phase from a coherent state that has not had its phase displaced. So that means that we want to calculate this expression here, which is the magnitude square of the scalar product between these two states. Now it's easy to show that this is equal to that. And now if delta theta is small, we can expand this expression, so we get this. And you see that, that the uncertainty in the estimation of the phase can be determined from the condition that the scalar product here squared is equal to 1 over E. Okay, so that gives us the uncertainty, which is 1 over the square root of the average number of photons, which is the so-called standard limit or shot noise. Now, is it possible to do better? Yes, it is. For instance, we can use the so-called noon states. They are states defined in this way here, so you see the name noon here. they have n photons in the upper branch or n photons in the lower branch, and in fact this state is a superposition of these two possibilities. These states were introduced within the trapped ion framework by Bollinger et al. That's Weiland's group, and in the optical interferometry framework by Jonathan Dowling. So this is the state then that we are going to use, and if we have this state going through this interferometer, you see that the n photons in the upper branch get dephased by this, so you have this reinforcement of the phase here by the number of photons, while if you have n photons in the lower branch, nothing happens, the phase is not changed. So now we have this changed state here, and you can now compare this state with the undisplaced state, which is this one, and the scalar product now gives you this expression, and you see that the cosine square vanishes and delta theta is equal to pi over n, which means scaling in 1 over n. That's the so-called Heisenberg scaling. So for this kind of scaling here, therefore for this kind of state, the precision is better for the same amount of resources. And the resources are here defined as the average number of photons used in this experiment. Okay? So that's the idea. You see that it is really the overlap between the two states, or if you want, the distinguishability between the two states that will determine this limit here of precision. Now, so what about the Kramer quantum, the quantum Kramer bound? Well, you proceed in the same way. Now the main difference is in the definition of this probability of finding the experimental result psi if the value of the parameter is x. That's given by the average of this operator here. And this operator is a generalization of the projection operators of von Neumann. We call it in general, the set of these operators we call a positive operator valued measurement. It's just a set of Hermitian positive semi-definite operators in Hilbert space, such that this relation is satisfied, and you see that from this definition that if this is true, then the integration of this probability density over all possible experimental results is equal to 1, as expected. Furthermore, the elements of a POVM are not necessarily orthogonal to each other, as in the case for von Neumann projectors. So it's a generalization of the von Neumann projectors. Now, we can follow the same derivation that we had in the first lecture, and we can show that if for this definition of the probability density, we still find the Kramer-Rao relation. We find that the standard deviation for the parameter to be estimated is equal to 1 over square root of n times f of x, where f of x is again the Fisher information, the same expression as before. The only difference is this expression for the probability density. Okay? So far, it's the same thing. Now, of course, if we are dealing with quantum mechanics, we know that given some measurement, we probably can do better. That's also true in classical physics, but usually one does not pay too much attention to it. But here we can ask, okay, what is really the ultimate precision limit if we do the best possible measurement, the one that actually maximizes this Fisher information? And if we ask that question, we are led to the so-called quantum Kramer-Rao bound, which depends on the quantum Fisher information that is defined by the maximization of the Fisher information defined before over all possible measurements made on the system. So we have now this expression here. That's the quantum Fisher information. And of course, if one looks at this definition, that in principle might look as an impossible task. You have to take the Fisher information, you have to imagine all possible measurements and maximize it. However, I'm going to show you that for pure states, you can actually derive an analytic expression for the quantum Fisher information. So this is then the expression, and now we are going to derive for pure states this maximization and show that a simple expression can be obtained for the quantum Fisher information. So in order to do that, let's consider this evolution, if you want, of the state of the system, which depends on the parameter to be estimated. So that's the state of the probe, remember, that we use to estimate the value of the parameter. So E of x is a unitary operator. We also define this auxiliary operator here, which is a function of this unitary evolution. And you see that if you define this operator like that, then the derivative of psi x with respect to the parameter can be written like that. That's the evolution operator. And then we can express this in terms of psi of x, which means applying the inverse of the unitary operator. And this gives us precisely this hx. And if you look at this expression here, you see that it looks like the Schrödinger equation. But of course, x is not time. X is just a general parameter. Could be a phase, could be a coupling constant. And h of x is in fact the generator of the unitary evolution E of x. Okay. Now, so let's start then with this definition of P of x that I showed you before. And what we are going to do that is, from this definition, we are going to reconstruct the Fisher information according to the definition we had before. So first, we differentiate this with respect to x. Of course, x is here and here, so it's this differentiation gives you this expression here. And by applying this derivative to this bra and this cat, we can use this relation here, so we get this commutator between this operator E and hx. And this expression here can actually be expressed as the imaginary part of this function here. Okay? This is just equivalent to the commutator. So now, since we have the imaginary part here, we could as well subtract a real function here and get the same expression, because this g of x contributes 0 to the imaginary part. Okay? So we now have this expression here, and from this expression here, we get the following. We square it, so we get this first line here. And now we just write this positive semi-definite operator as the product of its square root by the square root. So, and we notice here that we can apply Schwarz inequality just by separating this part from this one. So this will be smaller or equal than the average of the square of this operator times the average of the square of this whole thing here. So that's Schwarz inequality. So we get finally that the square of this derivative here is smaller or equal than this expression here. Now, put P of psi x to the left-hand side, integrate it with respect to psi, so you have here the Fisher information, and from this expression you have the Fisher information is bounded above by this expression here. Now, you see that these operators here just disappear just because you have the completeness relation, so we finally get this expression here. So now we want to find the minimum upper bound to the Fisher information, but we have this degree of freedom here. We can work on g of x, and in fact, we can do that through two steps. First, you see, we get this expression here. We can express it in terms of the state of the system, of the probe, if you want, before it undergoes the evolution that depends on x. And we do that by defining this operator here, which depends on the former operator h. This is like the Hamiltonian in the Heisenberg picture, you see? It's just the former h of x sandwiched between these two evolution operators. So since it's a Heisenberg-like operator, you can express this average in terms of an average using the initial states. And now it's, I leave to you to show that it's very simple. It's a functional derivative, if you want. You show that the maximum, that the minimum of this expression here, is obtained when g of x is equal to the average value of h. Okay? So it's a squared quantity, and this is a result. It's trivial to do. Is just differentiate this with respect to g, and equal it to 0, and then you find that. Okay, so just to have in mind what these things really mean, suppose that the evolution operator is like that, so it's an exponential, and the argument of the exponential depends linearly on the parameter. Then it's easy to show that this expression here is just this operator here. So if O, for instance, is Hamiltonian, then x is a time displacement, and u of x would be the evolution operator. Okay? So what I'm writing here could be the evolution operator, but could be something else. And this h of x could be the Hamiltonian, but could be in general any generator of the unitary operator. So if the unitary operator is a displacement in position, h would be a momentum, for instance. If the unitary evolution is displacement in phase, h would be an angular momentum, and so forth. Okay? So after doing that, we find finally that the Fisher information is bounded above by this expression here, which involves the variance of this operator in the initial state of the system. Okay? Now, so this is an upper bound of the Fisher information. What I'm going to show you now is that this upper bound can actually be attained by a proper measurement. And if you show that, then you show that the quantum Fisher information is actually given by this expression. So that's the way to prove it. Okay? So how do we do that? And I acknowledge that this slide is somewhat technical, but you have the papers here, and also they are on the web. You can look at that afterwards, but I think it's possible to follow this, and I will go over it slowly so that you can follow it, okay? So the trick is the following. I will consider that the outgoing state depends on some value of the parameter given by psi of prime, and we define a measurement given by these two operators, just two operators. One that projects the outgoing state into this state here, and the other that projects the outgoing state onto the orthogonal space. Okay? What I'm going to show is that the corresponding Fisher information, that is, the Fisher information corresponding to this measurement here, attains the upper bound derived in the last slide when x prime goes to x. Now, that's sort of intuitive. Okay? If x prime goes to x, that means that you are projecting the outgoing state into it. Okay? So because x prime is going to x. So if you find 1, and if you repeat the measurement over and over again, and it's always 1, then you know the value of the parameter. Okay? Of course, it's not a practical measurement, because you must know the value of the parameter in advance in order to build this measurement. So fortunately, this is not the only measurement that maximizes the quantum Fisher information. It's one of them, but it's good for formal purposes. At least I find one that leads me to this saturation of the bound. So I have these two measurements here. So I can write the Fisher information corresponding to this value of the parameter here as this expression. That's just the definition of the Fisher information, where now the sum over all the pi's is restricted to two terms. We have two terms here. So P1 of x prime is just the magnitude square of the scalar product between psi of x prime and psi of x, and P2 is 1 minus P1. So if I sum these terms and I use that P2 is 1 minus P1, I get this expression here. Now comes the technical part. If I set x prime going to x, you see that this goes to 0. The denominator goes to 0. And furthermore, this limit here also goes to 0. Okay? So we have an indeterminate expression here, 0 over 0. And therefore, we must use the trick which is due to a French, L'Hôpital's rule. Okay? So, and if you do that, we find that this limit when x prime goes to x is given by this expression. And now we can calculate this expression directly from the expression of P1. You just differentiate this with respect to x prime and let x prime go into x. Now remember that psi of x satisfies a sort of Schrödinger equation with the generator of the transformation. So if you make this derivation here twice, then it's a simple, you can show that it's just equal to the variance of the generator in the initial state. So you see that that's precisely the upper bound found before. So what we have just shown is that with this measurement here, you attain that upper bound. So, and that's therefore the best possible measurement. I should say one of the best, because we have not shown that it's unique. In fact, in general, it's not unique. Okay? There are other measurements. So in this way, we have shown that the quantum Fisher information is equal to 4 times the variance of the generator of the transformation. This variance is defined in this way. And also from the definition of H and from this expression here, it's also simple to show that this quantum Fisher information can be expressed in this way in terms of the outgoing state that depends on X. And this expression here is actually very useful, and we are going to use it a few times in these lectures. It is useful because many times you have some dynamical process, the probe goes through it, and you calculate the outgoing state. If you have the outgoing state, you plug it in this expression, then you have the quantum Fisher information. Okay? Now, let me give you an example of that. In fact, I'm going to give you some examples of application of this expression. First, optical interferometry. We know that the generator of phase displacements is just a number operator. So the quantum Fisher information should then be equal to 4 times the variance of the number operator, okay, because that's the variance of the generator. And if you have, for instance, so the expression that is like that, Ni here is the number of repetitions. I just set Ni equal to 1, otherwise we would have a square root of Ni here. I'm not writing N as the number of repetitions because I want to differentiate it from the photon number. Now, if we have a coherent state, then we know that the variance of the photon number in a coherent state is equal to the average photon number. So this is equal to that. And from this expression and this one, we get that the uncertainty in the estimation of the phase is bounded below by this expression here. So again, we have a standard limit kind of scaling. However, you remember that in the first lecture, we calculated this bound for the coherent state, for an interferometer, and we showed that it was bounded below by 1 over square root of the average number of photons. So we have an extra factor of 2 here, which did not show that there. How can we understand that? Well, you see, in the optical interferometer that I analyzed in lecture 1, we're actually comparing a dephased coherent state with a non-displaced coherent state. So we are using this coherent state on the other branch with the same amplitude than this one to measure the phase, to estimate the phase of this one. Now, what this result is telling me is that maybe there is a better way to do it, and of course there is. No? If you do homodyning on the coherent state, you'll get a better precision because you'll not have, say, the phase uncertainty of a coherent state with the same amplitude. In fact, homodyning amounts to using a coherent state with a number of photons much larger than the one in the probe state to measure the phase. Okay? So that's what this is telling us. And it's interesting to this remark because it tells us that the quantum Fisher information may actually tell us if the measurement we are doing is the best one to estimate the phase or whether there is a better one. Okay? And this points out to the fact that there is a better one with respect to the decision we had in lecture 1. Now, there is, of course, as we know already, a better way to do it, a better state to do it. And that corresponds to using a Nund state, as I mentioned before. Now, that's an entangled state. If we calculate the quantum Fisher information for this state, again, we have the same expression we had before, but then now the variance is equal to n squared over 4. So the uncertainty in the precision in the determination of the phase is bounded below by 1 over n. So that's the Heisenberg limit, and you see it coming out from this formalism. Example 2, spatial displacement. The spatial displacement corresponds to this unitary operator applied to the initial probe state. That's the momentum operator. H, given by the expression that we had before, is just equal in this case to the momentum operator. And therefore, the quantum Fisher information is 4 times the variance of the momentum in the initial state. And that gives me, for the Kramer-Rao bound, an expression like that. The variance in the estimation of this displacement is bounded below by this quantity here that depends on the variance of P in the initial state. Now, so this is what we are estimating. That's the displacement of the state. Now, if we have a coherent state, which is shown here, the variance in momentum with this scaling, with this definition of units here, is equal to 1/2. That gives me, for the variance of this in the estimation of this parameter here, also 1/2. And because it's a coherent state, this saturates the Kramer-Rao bound. Okay, this is just this bound here. So a coherent state saturates the Kramer-Rao bound. However, it's not the best state, and that's quite clear geometrically. If we use a squeezed state, we can have a better precision in the estimation of x. We just have to increase the variance in P and decreasing the variance in x. So we'll get a better precision. Furthermore, since this is still a minimum uncertainty state, the squeezed state will also saturate Kramer-Rao. It's a Gaussian state, it saturates Kramer-Rao. And this makes also a connection with what we saw in the lecture 1. Both are Gaussian states, and we have shown in the first lecture that Gaussian states lead to the saturation of the Kramer-Rao relation. Okay? An important remark, you see, this looks like the Heisenberg uncertainty relation, but it's not. And it's not because x is a displacement. It's not an operator. And indeed, you should remember that in principle, if you have many measurements, we should have a square root of ni here below, which means that for some given value of delta p, we can measure the uncertainty in x as precise as we want, just by repeating the measurements. Okay? So this is not Heisenberg, just because this is a parameter. Okay? Sometimes this has been called generalized Heisenberg relation. I don't like this name because it may add to the confusion. It's just estimation of parameters, Kramer-Rao. So now I'm going to show you how this theory applies to entangled states. And in fact, I'm going to show you that entangled states help us to reach the Heisenberg limit. So first, some rappel sur l'intrication. Let's consider a multipartite system of n particles. And then the state of the system is defined in this product space here. That's the tensor product of the individual Hilbert spaces of each part. A pure state describing a system with many parts is considered to be separable or non-entangled if it can be written as the product of the states corresponding to each part. This means that it's possible to assign a state to each subsystem. The most general state in this space is just a combination of these product states here. And this state here in general is not a product. It cannot be written as the product of states of each part. Examples of entangled states or non-separable states are these states here. So they cannot be written as products of the state of spin 1 with spin 2. These are the famous Bell states. And you see that if we, in this example here, we ask about the state of spin 1. Well, what we can do is that it's 50% in state 0 and 50% in state 1. That means complete ignorance. So in this example, one has maximal ignorance of the state of each qubit, and because of that, it's called a maximally entangled state. Okay? And the ignorance is a measure, actually, in this case, of the entanglement of the state. This measure is actually associated to an old remark by Schrödinger, which was quite modern, actually. So Schrödinger, in this paper he wrote about entanglement, that this is the reason that knowledge of the individual systems can decline to the scantiest, even 0, while that of the combined system remains continually maximal. Best possible knowledge of a whole does not include best possible knowledge of its parts, and that is what keeps coming back to haunt us. And I can assure you that entanglement haunts scientists even nowadays. Okay? In fact, there are mathematical properties of entanglement that are still open. Now, so this is entanglement, and now let me go back to quantum metrology, and let's discuss now possible strategies for quantum-enhanced metrology. So we know that the quantum Fisher information is given by that. That's the best we can do for a given incoming state of the probe. So in order to increase this precision, we need to increase the variance of H. That's what happened, for instance, with the displacement. The squeeze state increased the variance of the momentum and therefore increased the precision in the estimation of the displacement. So if we have, if the spectrum of H, I call it Hamiltonian, but not necessarily Hamiltonian, is discrete and bounded, we can maximize this variance by using an optimal state, which is given by superposition of the eigenstate corresponding to the maximum eigenvalue of H and the eigenstate corresponding to the minimal eigenvalue of H. So that means that the dispersion is as large as possible. And if we do that, then the variance in this operator here is given by this expression here. And therefore, the precision in the estimation of the parameter x is given by this expression according to Kramer-Rao, where he is the number of repetitions of the experiment as before. So this is for one probe. An important question, what is the best strategy if one has n probes? So this was discussed in this paper here. We have 4 different possibilities. This we call, say, classical. We start with separable experiments, different experiments. We make independent measurements. This is classical quantum, separable inputs, but then somehow the measurement is a global measurement. This is quantum classical, initial entanglement of the incoming states, separated measurements, and finally quantum, entanglement in the initial states, and global measurements. Now let's analyze each of these cases. First, let's take this case here in which you have entanglement just at the end, at most. So the evolution operator corresponding to these probes here is just the product of the evolution operators of each probe. So we have here a generator of this global unitary, which is just the sum of the generators for each probe. Suppose we start with an initial state, which is just a product initial state, like this one. Then the variance of this H here, the global H, is just equal to the sum of the variances of each individual generator. And this means that if you have this state here, then the variance is given by that. So even if we pick up each of these states as the optimal state, the variance will be proportional to n, just the number of systems used, and therefore the precision in the estimation of the parameter will be given by this expression, which depends on the square root of n. Okay? So by using either this scheme or this scheme here, we get just the standard limit for the precision. Now, second situation, we entangle the initial states, and we do either separate measurements or global measurements at the end. Again, the unitary evolution is given by the product of individual evolutions. These are the individual generators. This is the global generator. And now we want to maximize the variance in this state here, which is an entangled state. Now, this is like calculating the variance of the number operator in the null state. And the result is this one. It depends now on n squared. And therefore, the precision in the estimation of x is given by this expression here, which is inversely proportional to n. So by using incoming entangled states, we get a dependence on n. And in fact, we do not need to do global measurements at the end. It's enough to do separated measurements to get this enhancement. So this is showing that if we use separate states to start with, we don't get an enhancement. We need entangled states to start. And that means also that entanglement is necessarily sufficient for reaching the Heisenberg scaling for pure states if those previous conditions are met. The generator has a discrete spectrum and a bounded spectrum. Okay? So entanglement is very important, and let me give an example of that. So that's a familiar example here. It's in atomic spectroscopy. So we prepare n qubits, so n-to level atoms, in this superposition state. We assume that the evolution of each qubit is given by this expression. So if the atom is, or the qubit is in state 1, it undergoes a dephasing. If it is in state 0, there's no dephasing. Therefore, the initial state psi plus becomes this state here after the atom crosses this region here, okay? And it may undergo this dephasing because it interacts with some field in this cavity, like it was done here at ENS, or because it is not precisely resonant with these two regions here, which are called Ramsey regions, which place the atom in the superposition state. Okay. Now, you must now choose a proper measurement to estimate this angle phi. And we are going to choose the one associated to the Pauli sigma x operator. In fact, we are going to show that that's the best measurement in this case. So the measurement of sigma x has two possible outcomes because it's a spin operator, it's +1 or -1. The eigenstates of sigma x are given by this expression here. So the probability of finding each of these two eigenvalues are given by this expression here. It's just a projection of this state onto the eigenstates of sigma x, and this is equal to this expression here. And now we have the two probabilities, so we can calculate the Fisher information. Just calculate the sum here, and we find that for this case, the Fisher information is equal to 1. Okay? Now, let's see what the quantum Fisher information tells us. So the quantum Fisher information is given by 4 times the variance of the generator. Now, we know that the generator of the phase displacement is given by this operator here. It's 1 plus sigma z over 2. If you apply that to 0, that gives you 0. If you apply it to 1, it gives you 1. Okay? So this is the generator of the phase displacements. Now, we can calculate now the variance of this generator for the initial state plus, and that gives me 1 over 4. Now you see, according to this expression here, the quantum Fisher information then should be equal to 1, which coincides to this expression. Okay? So this shows that indeed this measurement is the best possible measurement. It leads me to the quantum Fisher information. Okay? And not by chance, this was the measurement done here at ENS for the quantum non-demolition measurement, for instance, of a field in a cavity. So the intuition the experimental intuition many times is as good as the quantum Fisher information. Okay. Now, so let's see now what entanglement can do to us. We prepare now these n qubits in a GHZ-like state. So again, we consider the same evolution as before. The state 0 does not change. The state 1 gets defaced. And we define this state here, plus n, as the superposition of n zeros and n ones, like this. See? A GHZ state would be a special example of that with 3 qubits. And we define also minus n as the superposition with a minus sign. So after the evolution, this initial state here becomes this one. You see here the phase reinforcement already. But let's just apply the theory we had before. Now, in order to estimate the phase, we choose this observable here. It's just the tensor product of sigma x operators, which means that we are doing independent measurements on the outgoing atoms. Okay? It's not an entangled measurement. Now, the eigenvalues, the eigenvectors of this operator here are plus or minus n, as defined here. And the probability of getting each of these eigenvalues is given by this expression here, which is given by this expression. Okay? So you have here the enhancement factor. Now again, we have the probability, so we can calculate the Fisher information, and that is equal to n squared in this case. Yeah? Now, again, we want to show that this is the quantum Fisher information, that that's the best you can do. In other words, that that's the best possible measurement. So in this case, the generator of phase displacements is just the sum of the phase of the generators for each atom. So now the variance of this operator in the initial state of the system is equal to n squared over 4. And therefore, this measurement leads indeed to the maximum value of the Fisher information, because the quantum Fisher information is 4 times this, which coincides with that. Okay? So this shows that separable measurements are enough to get to the Heisenberg limit. You don't need an entangled measurement. Another example, recent one, it's the use of entangled atoms to increase the precision in the measurement of, for instance, a phase. So this is a paper which was published now in January and by the group of Kasevich. And the idea is the following. You have here a cavity. These are semi-transparent mirrors. This beam here, which is painted in red, corresponds to this wave here. This is actually a lattice potential. Yeah? It traps atoms in this minima of the intensity. You have here a probe field that's represented here by these blue waves. It has a wavelength which is half the wavelength of the lattice field. So you see that that's clearly shown here. And this field is such that the atoms that are trapped by the lattice field see the same field. Okay, so that's an important requirement. So this field interacts in principle homogeneously with all these atoms. Now, this field is actually tuned so that its interaction with these atoms is a dispersive interaction. These are rubidium atoms, and these are clock states of the rubidium atoms. That means that they are insensitive to magnetic fields, a magnetic quantum number equal to 0. Okay? And that's the configuration. Now, the frequency then of the probe field is sensitive to the state of the atom, just because of, if you want, a refraction index effect, since this collection of atoms is interacting dispersively with the field. This is like a material with some refractive index. And if you insert some slab of refraction index in the cavity, this is going to change the frequency of the field in the cavity. So by measuring the frequency of this field by homodyning process, you can know what is the state of the atom. So that's actually a measurement of Jz, of the Z component of the angular momentum of the collection of atoms. Remember the first lecture, I defined to you this atomic angular momentum. In fact, I even use the atomic angular momentum in an optical interferometer, because you can deal with an optical interferometer in terms of this Schwinger angular momentum operators. So you see, this is actually a quantum non-demolition measurement of the angular momentum of the atoms. It's quantum non-demolition precisely because this field is not resonant with an atomic transition. So there is no photon absorption here, and there is no atomic transition in first approximation. Okay? So that's the idea. Now, this is very similar to what was done here at ENS. Here we had a QND measurement of a field using atoms, and this measurement leads to a subpoissonian field, eventually to a Fock state of the field. Here we use a field to make a QND measurement of the collective atomic state. That leads to a squeezed atomic state, and the remaining width is due to two facts. First, there is a short noise associated to the measuring field. Second, there are Raman processes that flip the spins. Okay? So, and that contributes to the width. Okay? These are the main factors. Okay? But you know, it's quite analog. You just interchange atoms and fields. Now, I told you about atomic coherent state before, and I want to be more specific about that. So how do you produce such an atomic coherent state? Well, you can apply a pi/2 microwave pulse to the atoms, which are initially in the ground state, and you get a resulting state like this. So this means that each atom, in this case, is an eigenstate of sigma x, and this is a product state. It's a non-entangled state. It's a special kind of coherent state. And for this state, you see that the average of Jx is equal to n/2. Of course, it's an eigenstate of Jx. And also from this commutation relation between the components of J, we have this uncertainty relation here. And for this state here, it's easy to show that the standard deviations of Jz and Jy are equal to square root of n/2. And therefore, this uncertainty relation is satisfied as an equality. Okay? So this corresponds, say, to a coherent spin state. And the value of these variances here is called the projection noise, which is the equivalent of the short noise for the electromagnetic field when you are measuring atoms. Now, the bound on the uncertainty in the phase displacement is given, you can see this geometrically here, basically is given by the standard deviation of Jz divided by the length of this vector, which is average of Jx. And from these results here, you see that that's equal to 1/square root of n. Okay? So with this kind of state, we get a standard deviation. Now, using, and that's a typical distribution of counts, and which gives a dispersion in the values of Jz. A typical distribution for a coherent spin state. Now, of course, from this result here, you see that this uncertainty can be reduced by 10 by multiplying n by 100, of course, because it depends on square root of n. Now, by using the QND measurement I mentioned before, they are able to produce squeezed states of the field. So these two spheres, which are actually Bloch spheres, show that compare two squeezed states, one which is on the equator, and the other that undergoes a small deviation from the equator. It's an angle of 660 microradians, and the corresponding distributions of values for Jz are given here, and compared to an under-squeezed distribution in the background. The figure of merit they use to quantify the metrological improvement is this one. You see, this is a product of two factors. The first one corresponds to noise reduction. You are comparing the standard deviation, in this case, with the standard deviation for a coherent state. And the second factor represents coherence loss. That means the length of Jx is not as big as the one for a coherent state. It can be reduced because of loss of coherence. Now, if you keep this constant, you see that if you reduce the standard deviation, you increase chi square. For a coherent state, chi square is equal to 1. In the experiment, they obtained chi square equal to 100. That corresponds to 20 decibels. And this is equivalent to actually increasing the number of atoms with the coherent state by 100. Okay? That's why this figure of merit is used. It tells you immediately what is the multiplication of number of atoms you have to do in order to get the same precision. Now, that's also a nice system to understand possible advantages of these metrological improvements. You see, if you increase the number of atoms, you start having collisions between atoms. And in fact, there is typically an upper bound to the number of atoms that can be employed in cold atom sensors. In this experiment, they use up to 7 times 10 to the 5 atoms. And this is just an example because to increase the visualization here, but they got a single shot phase resolution of 147 microradians, which is actually a record, it seems, in this field. Okay? So that's an example of how squeezing and entanglement, because the squeezed state is entangled, can be helpful in this domain. Now, I want now to tell you a bit about the application of quantum metrology to weak value amplification. And I'm going to show you that this theory of quantum metrology helps us to understand what weak value amplification is about. In order to do that, let's start with just the usual measurement scheme, which was studied by von Neumann a long time ago. You start with some interaction Hamiltonian between the system to be measured and the pointer, which is given by this expression. You see I have a delta function here, which means that it's a fast interaction between system and the measuring apparatus. The corresponding evolution operator is given by this expression here. And here we neglect the free evolution just because this interaction occurs in a very short time. So we don't care about free evolution. So A is system observable. We assume this operator here to have a discrete and non-degenerate spectrum, just for simplicity. So its eigenvectors and eigenvalues are written down here. Me is the meter observable, and we assume for the meter observable a continuous spectrum. We take the initial state of system plus meter as a separable state. It's just a product state. And they undergo some interaction, which is given by this expression here. And then I look at the meter, and I look at the value of the pointer observable, which is actually canonically conjugate to m. So let me give an example of that. Suppose m is the momentum, and x then the conjugate variable will be the position. So if m is the momentum, you see that what the evolution is going to do is to displace the pointer in position, depending, of course, on the eigenvalues of A. In fact, if you start with an initial state of A, which is given by that, and an initial state of the pointer, which is given by that, and if you apply this evolution operator to this initial product state, then you see that A acting on this will just produce the corresponding eigenvalues, and then you'll have some exponential, which depends on P and on the eigenvalues, which will displace these X eigenstates here. So you get here an entangled state between the state of the system and the pointer, and by looking at the position of the pointer, in principle, you could know the state of the system. You measure the pointer, the position of the pointer, you project the pointer into one of these eigenstates of X, and this means that you know AI. Now, that's true for the usual measurements. For the so-called strong measurement, a requirement for that is that the distance between nearby eigenvalues here is much larger than delta x, the width of this pointer state. If that's not true, you have a weak measurement, so by measuring the pointer, you will not be able to tell precisely what the eigenstate of A is. Let me give a simple example of that, which has to do with Stern-Gerlach. So this is an example of a strong measurement. You can really differentiate between the two positions of the beam, and therefore, from that, you can, for instance, estimate the magnitude of the magnetic field, say, of the coupling constant between the spin and the magnetic field. This is a weak measurement in which you do not differentiate between the two wave packets, so you're not able to precisely estimate the value of the coupling constant between spins and the magnetic field. So the idea of weak value amplification, which was proposed a long time ago by Yakir Haronov and collaborators, is the following. You do a post-selected measurement. What does it mean? You see, here we have the scheme we had before, but now we added this branch here. So you measure X conditioned to the measurement of A in a state psi f. That's the idea. That means, of course, that you are losing data. Whenever you measure a state here which is not psi f, you don't do anything to the pointer. Now, so again, psi f is given by this expression here in terms of the initial states. So that's the evolution we had before. Now, we can calculate the unnormalized meter state after post-selection, assuming some weak interaction, in the following way. So this is the initial state, this is the evolution, and now I project this final state here onto the post-selected state, the state we want to post-select, and now that will give me the post-selected state of the meter, okay? Because I have already projected onto the state of the system. So the post-selected state of the meter, non-normalized here, I'm not normalizing this, can be written in this way, expand this exponential, assuming weak interaction. So the first term is given by that. Now, you see that this one here will just give me a scalar product between psi f and psi I. So I put it outside this parenthesis here. So here's the scalar product. And of course, I'm going to divide this matrix element of A between psi f and psi I by the same expression. So I get this expression here. Okay? So you see, by doing that, I got rid of psi I and psi f. They only show up in this term here and in the matrix element of A between psi A and psi f. Now, this expression that shows up here is a funny expression. It is the matrix element of A between psi A and psi f divided by the scalar product between psi A and psi f. That's called weak value of A. You see from this expression here, now we can go one step further. We can reconstitute, if you want, reconstruct the exponential, again, assuming a weak coupling, and then we get this exponential here. And from here, you see now that this is a displacement of the pointer by the amount which is given by the weak value. Okay? Now, so that's the original idea. Of course, this could be much larger than the average value of A if this scalar product here is small enough. That is, if psi f is almost orthogonal to psi I. However, there are some conditions for all these manipulations to be true. And we are using here perturbation theory. And one condition is that this expression here should be much smaller than 1, where delta m is the width of the pointer state. Okay? So this is an important condition which shows that the amplification cannot be too large. Or if you want, if you want to increase that, you should increase the width delta m. Remember that the measurement is only conjugate variable, so decreasing delta m means increasing, say, the spread in x, if m is the momentum. Okay? So that's the way to satisfy this relation and increase the weak value. You have to decrease delta m, and therefore increase the width of the wave packet for the conjugate variable, which is actually used for the measurement. That means very imprecise measurement. Okay? So that's the idea. Furthermore, you can calculate the probability of post-selection. That's just the norm of this state here because it's not normalized. And that's given by this expression here. It's just this is the post-selection of the evolved state onto the state of the system. And if you expand this in terms of g, you see that the first term is 1, and then you have corrections of the order of g squared. Now, if psi f, psi y is very small, that means that the probability of post-selection is very, very small. And we might then wonder what quantum metrology has to tell us about this, because after all, that means that you are spending lots of resources in order to get this expression. Okay? Resources include all the data that are not taken into account. Okay? Now, just note that the normalized expression for this final state of the pointer after post-selection is given by this. It's just the normalized state divided by the square root of the probability, and this can be written like that. We are going to use this in the following. Okay? Now, example of weak value amplification. It's the quantum version of random walks. So we consider a particle with spin 1/2, which is moving on a one-dimensional lattice. And we assume that the width of the wave packet in position space is much larger than the lattice parameter and is centered around some point x0. Okay? So you see again this notion of weak measurement is present. If you want to measure a random walk, but the width of your pointer is much larger than the elementary step. Okay? Now, this spin works as a quantum coin for the movement of the particle. If the spin is up, the particle moves right. If the spin is down, it moves left. And the dynamics can be described by this evolution operator here. See, this is the spin operator. This is momentum or displacement operator. Spin up, displacement by L. Spin down, displacement by minus L. Okay. Now, of course, here there is no quantum mechanics up to now. This quantum coin could be a classical coin. But quantum mechanics comes in when we write down the initial state as this one. Okay, so this is a superposition state. So the final state, just applying this unitary evolution, then will be like that. You see again, you see the correlation. Spin up, right, spin left. Spin down, left. And this state here is centered around x0 plus or minus L. So now we do the following. Suppose one measures this state here along the direction theta phi in this spin state. And you see that if you measure along this direction, these two states in the configuration space will be put in a superposition, okay? Because we have measured the spin. And this means that we could have interference between them. And in fact, what I'm going to show you is that weak value amplification has to do with precisely this interference between the states of the pointer. Now, so we measure along this direction. Now, just to be precise, I'm not going to do the calculations here, but just tell you the results. Assume that the spin minus h bar over 2 is found when I measure along this direction. And I choose phi as the argument of this ratio here, which depends on this coefficient. So phi determines also the direction where I'm measuring. Then one can show that if we choose theta in this way, with epsilon much smaller than 1, this direction theta phi is almost orthogonal to the initial direction of the spins. Okay, so these are the conditions for doing this almost orthogonality between the final state and the initial state. So you see the spin here is the system, the state of the point, the state in configuration space is the state of the pointer. Now, these are the numerical results for this wave packet. This is the initial wave packet. We take it as a Gaussian. It's full line here. We take here epsilon equal to 0.1. And the elementary step is taken as 0.01. Look at the wave packet after 10 steps. You see that the peak of the wave packet is in -2. That means a displacement of 2 after 10 steps. And you see 2 is 200 times the elementary steps. So you see that by successively doing that, you measure, you put the spin in the superposition, you measure along that direction, then you put again in the superposition, you measure again, you can go much faster than by using the classical random walk. In fact, if you don't do these intermediate measurements and just wait for the system to evolve, it has been shown after this paper that the distribution of the quantum walk is quite different from the distribution of the classical random walk. The classical random walk gives you a Gaussian centered around the origin. The quantum walk gives you 2 peaks apart from the origin, and that's why the quantum walk has been considered by some people as a possible algorithm for computation. In fact, the classical walk is one of the algorithms used for computation, okay? Because of the speed up, which is already manifest in this case. Now, so this is an example, but then again, we know that the probability of finding the spin along this direction given by this angle is very small. So is it worth going through that? Because after all, we are losing lots of data, and in a standard measurement, we could use all of them and then increase the precision as well. So how do we deal with this problem from a quantum metrology perspective? So again, you see the evolution operator is like that, and now we just turn the crank again, use the theory of quantum metrology. From this evolution operator here, we know how to calculate the quantum Fisher information. It's just the variance of this generator here, A cross M. This is equal to that. And I'm going to assume for simplicity that the average of M, see these averages are taken in the initial state, and I'm going to assume for simplicity that the average of M in the initial state is equal to 0. So it's a balanced meter, okay? So that's the quantum Fisher information. And now I have to have a set of operators that translate this post-selection procedure. And the operators are these. What this is telling me is the following. If I find the system in this post-selected state, then I must measure the pointer using this complete set of operators here, which are in general POVMs. Okay? Now, if I don't find the system in the post-selected state, so that's you find it in an orthogonal space, then I don't do anything to the pointer. Okay? So this is the collection. This is the POVM, which I use for this kind of measurements. Now, if I have the POVM, I can calculate immediately the probabilities. The probabilities correspond to averages of these of the measurement operators on the final state of the system that is obtained by applying this evolution on the initial state. So I just have to take the averages on the final state of the full system and operator on this, with these operators here, and we find then a set of probabilities which is given by that. You see, this is just the average of that in the final state, and this is the average of that in the final state. So now we have a set of probabilities, and again, to calculate the quantum Fisher information, or the Fisher information, say first, we turn the crank. We have the probability, so we can calculate the Fisher information. Now, this post-selection probability, I showed you before in the last slide or so, that it satisfies this expression here. And it's easy to show by using that this probability pi here can be written as a product of 2 probabilities. One is the probability of post-selection, and the other is just this average here. And this average here is the average, is the probability of measuring this operator here, or this of getting, say, this experimental value if the pointer is in the state phi f. Okay? So by writing pi like that, I'm separating pi into 2 parts. One, which is the post-selection probability, the other, which is the probability of getting some experimental result I if I measure the pointer, independently of the post-selection. Okay. So again, some simple algebraic expressions. So this is the post-selection Fisher information. Okay. This is the when I don't get the post-selected state. This is when I get the post-selected state. And now it's a simple algebra to go from this expression to this one, which for us is much more interesting. In fact, you just replace pi by this, you calculate the derivatives, and you find this. So look at this expression here. So this expression corresponds to the Fisher information associated to measurements on the pointer, multiplied by this post-selection. So this is really the Fisher information degraded by the loss of statistical data, okay? Because I have this probability here which reduces the value of the Fisher information. So it's nice because you see this formalism does take into account the loss of data associated to the post-selection. Okay? It shows up naturally in the expressions. And this is a very interesting term because it depends only on the post-selection probability. This is actually the information on the coupling constant G encoded in the post-selection probability. Well, if this was the only term, that would be great because you just have to count the number of times you get the post-selected state, and then you get information about G. But you'll see that the situation is not so simple. So by doing that, we have written the post-selection Fisher information as the sum of these two terms. Now, on the other hand, we know how to express the quantum Fisher information for the meter, corresponding to best possible measurement, by using this expression which I announced in a previous slide. I told you that was an expression I was going to use. So we know what is phi of G, and therefore we can calculate the quantum Fisher information associated to phi of G. And what we have done, in fact, in this work, is to calculate these things using perturbation theory, okay? Because we have done that in very general terms. So these are the two expressions. I have now slightly changed the notation. Now the post-selected Fisher information is given by the sum of two terms. One is the quantum Fisher information associated with the meter, which I can actually calculate, at least in a perturbation way. And this is the information on G encoded in the post-selection probability. Now, the perturbation theory here is tricky. Don't scare. I'm not going to give you the details, okay? But it's sufficiently tricky that people have not noticed before. That, in fact, we have two small parameters here, and therefore there are two different perturbation theories that can be calculated. One parameter is this overlap between the final post-selected state and the initial state, and the other parameter is the coupling constant. So if you want to know what happens when the two states become almost orthogonal to each other, you cannot just use perturbation theory in G, because delta is a small parameter. So that's what we have done with these people here. Well, some of them you know, Bier, Gabriel and Bruno Escher are two former students of mine. Matos Filho and Ruinem Matos Filho and Nissim Zaguri are two colleagues of mine. Nissim has come here sometimes. And I'm going to give you the results. Okay? So in this paper, we show the following, that there is, in fact, an optimal post-selected state. And the post-selected state is given by this expression here. It's obtained by applying the system operator to the initial state and normalizing this. And then if you do that, we show that the limit of this post-selected Fisher information here goes to the quantum Fisher information when the coupling constant is very small. Okay? So that's good news and bad news for weak value amplification. It's good news because that means that with sufficiently small G, if you choose the post-selected state correctly, and this has not been done in many experiments realized up to now, then this post-selected Fisher information goes to the quantum Fisher information, which gives you the best precision you can get. Okay? Of course, it goes to that, but from below. Okay, that's important. It goes to that, but from below, because we know that the quantum Fisher information is the top, is the best you can do for the best possible measurement. And the weak value post-selection is just a possible measurement. Okay? But it goes to that. However, the contributions of these two terms depend on the region of parameters. So if this is true, remember this was the condition for making that manipulation with the exponentials. So this is actually the condition of validity of the weak value theory. We showed that in this case it is this term that contributes. So the quantum Fisher information associated to the meter goes to the quantum Fisher information for this kind of measurement and for the best possible measurement. On the other hand, if this condition is true, that means outside the region of validity of weak value theory, according to that expansion, then it is this term that goes to the quantum Fisher information. Okay? So in particular, if the overlap between the final state and the initial state is too small, you don't get any information from the meter, but you may get information from the post-selected statistics. Okay? Furthermore, if you look at the weak value, which remember is given by this expression, and you replace psi f by this expression, you get this. And this is larger or equal than the average value of A. Okay? That's a simple inequality. And that means that there is indeed amplification for this choice of psi optimum. Okay? So the weak value is larger than the average value of A. Okay? Now, so let me give you an example for a spin measurement. So, and this is going to be my last slide. That could be, for instance, Tergelac measurement, where spin interacts with a magnetic field. So in this case, A is equal to sigma z, A squared is equal to 1, and the evolution operator is given by this expression here. Depending on the value of spin, you have displacement, say, in momentum, if you want, up or down. The psi optimal in this case is given by this expression, as I mentioned before. Since A squared is equal to 1, this is just equal to sigma z applied to psi I. Now, sigma z applied to psi I on the Bloch sphere means a rotation of pi around the z-axis. So if you start with psi I like that, this is psi f, just a rotation of psi around the z-axis. Now, we take as the initial state of the meter a Gaussian distribution of the eigenvalues of m with some width given by this expression here. Okay? That's the standard deviation. Remember that the average of m we take is equal to 0. The weak value in this case is given by a simple expression. A squared, remember, is equal to 1. So this is just 1 over the average of sigma z in the initial state. But sigma z applied to psi I is the final optimal state. So this is just equal, the weak value is the inverse of the overlap between the initial state and the post-selected state. Okay? So the smaller this overlap, of course, the larger will be the weak value. Now, let's see what happens when we increase this theta I, keeping psi f as the best post-selected state, from this angle here to the equatorial plane. This is shown in this plot. This plot shows the Fisher information as a function of theta I. That's the total Fisher information. This upper plot here refers to the meter Fisher information. This lower plot refers to the post-selection probability Fisher information. So we start from this position here, which corresponds to this angle. And now I'm going to increase this angle, but at the same time keep always psi f as sigma z times psi I. So here we are increasing. This is becoming orthogonal. And you see that the Fisher information gets transformed, not the total one, but the terms that contribute to it. Initially, it is the meter Fisher information that contributes the most. As theta I goes to pi over 2 and the two states become orthogonal, we get more and more contribution from this statistical or from the Fisher information associated to the statistics, which shows that this second term in the Fisher information becomes important. And this transition region corresponds precisely to G, to this expression equal to 1 approximately, which is precisely the transition between the validity of the weak value approximation and this other region. Okay? So, moral of the story, if you want to do an experiment with weak value approximation and you want to explore these extreme conditions in which the final post-selected state is almost orthogonal to the initial state, don't look just at the pointer, look also at the post-selected statistics, because finally your information is coming from there. This is the motion of the pointer as a function of theta I for that example. You see that when you get to pi over 2 or minus pi over 2, the motion of the pointer is 0, which means that you don't get any information on G by looking at the pointer. The pointer stopped there at the 0 position. Okay, so there is some debate about the value of weak value amplification, and there are some arguments against it. As many debates in physics, this is a tough debate. So these authors argue that they say we prove that post-selection, a necessary ingredient for weak value amplification, decreases estimation accuracy, and moreover, arranging for anomalously large weak values is suboptimal strategy. In doing so, we explicitly provide the optimal estimator and so forth. Okay? That's in agreement with what we have shown. We cannot go over the quantum Fisher information. However, the strategy of going to these extreme values is suboptimal if you just look at the pointer. But if you look at the other information that comes from the post-selection statistics, it's okay. Okay? But in any case, it's comparable with standard metrology. And then there is some argument for the weak value approximation from this group. And their argument is that if you have noise types like detectors transverse jitter, angular beam jitter before the interferometer and turbulence, that corresponds to the measurement of a small shift of a mirror by looking at the light scattered by it. And they say that in these cases, weak value amplification can be useful because you can shorten the path followed by the light and therefore have reduced the errors due to these other effects. Okay? But the debate is still on. On the other hand, I hope I have shown you that quantum metrology gives us a firm stand on this analysis. Okay? Now, in the third lesson of this course, we are going to extend this treatment to open systems. That means that we are considering, for instance, a lossy optical interferometer or an optical interferometer with diffusion, or yet estimation of force with the help, say, of a damped harmonic oscillator, okay? In which case this method cannot be directly applied. The nice expression we derived for the quantum Fisher information was good for pure states. For mixed states, you need other kinds of techniques, and I'm going to discuss that in the third lecture. Thank you very much for your attention.